In this lesson, we are going to look at a growth and a decay word problem. I'm going to read it to you, and basically all we're going to be doing right now is instead of creating the problem ourselves, we're going to be looking at the graph and being able to read the graphs. And so the first problem is a decay by half-life, it's called. The pesticide DDT was widely used in the United States until its ban in 1972. DDT is toxic to a wide range of animals and aquatic life and is suspected to cause cancer in humans. The half-life of DDT can be 15 or more years. Half-life is the amount of time it takes for half of the amount of a substance to decay. Scientists and environmentalists worry about such substances because these hazardous materials continue to be dangerous for many years after their disposal. Now this is actually something, if you want to research, look up articles online. DDT was a big deal back in the 70s and 80s. They were really worried. It used to be used commonly in different products, and it was found to be toxic, and so people started to suspect that it was going to cause problems. They thought, it causes cancer, it's having problems with our water, which is going to impact animals plus humans. And so they studied it for quite a while, and you can look up a lot of research on that. But what's scary about DDT is even though it was banned in the 70s, so 1972, that is actually even before I was born, surprisingly. If you look back that far when it was banned, it's still around today because it's got a half-life, which means it takes 15 years for half of it to go away. So if you look at this graph here, you're given your x and y axis, what they represent. So the x-axis is each interval in 15 years. So when you look at this 2 right here, this is really 30 years, and then 60, 90, because each one would be 15 years. And then, so that's the number of years. So this each interval is 15 years. And then the side here, this is the grams of DDT remaining. So you're given that. It says after 60 years, estimate how many grams of DDT remain. So I want you to think about right now, from 1972 until 2013, so about 2012, right? It's been 40 years. In 40 years, where would that be on our graph? We'd say probably right about here. So look at the grams of DDT remaining. It's still over 20 grams. So this substance that has been banned since 1972 is still showing up when we take soil samples or water samples in areas that had this, which is why the environmentalists and scientists are so nervous about it, because it's still causing problems in our system. One of the things they look for, even for such things as recycling or how we are contributing our carbon footprint, is you're looking at things that don't break down, which is why we have recycling programs in our town that we recycle cans and plastics and all of those things, because we want to reuse them because they don't break down very easily. DDT is the pesticide that does not break down, and so it is still around even though it's been banned for 40 years. For 40 years we still have grams of that remaining. So thinking about that, it could still be causing cancer or other issues in humans, in aquatic life, in animals, whatever you want to talk about. It's kind of interesting to study things like this, and this is what the scientists would do with this. So this is an example of exponential decay, and that's where the half-life term comes in. So all you're being asked to do, if you kind of understand that problem, is they just want to know after 60 years how many grams remain. So it says estimate, notice, because we are reading this off of a graph. Right here, sorry. We're reading that off of a graph. So when I go to 60 years, I already labeled that right here, didn't I? So we're going to estimate where we think that is. If I draw that line across, I'm going to say, I think it's 6 or 7. So you can pick either, it's an estimate, so I'm going to say approximately, and I'll just say 7 grams. So there's approximately 7 grams remaining after 60 years. And notice, if we were to keep going, this is always adding 30 years, right? At 150 years, we're finally getting down to maybe where there's not much remaining. 150 years, I mean, that's a couple of lifetimes for people. So if you look at that, that's kind of a big deal. So if you ever were to study this in science, or if you were going to be an environmentalist, this would be something that you would look at, and you actually do quite a bit with exponential growth and decay problems. So that was reading the graph. The second one we're going to do is growth by doubling. This one's kind of creepy, I think, actually, when we look at it. It says, one of the most common examples of exponential growth deals with bacteria. Bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells, thus doubling. For example, if we start with only 1 bacteria, which can double every hour, by the end of 1 day we have over 16 million bacteria. Why I say this one is kind of gross is I think about how you guys share desks with people in our classroom, and so if someone first hour sneezes on the desk, and there's some bacteria there, think of those doubling every hour, and you're sitting in that desk fifth hour that same day and it hasn't been cleaned. Ugh. So no wonder we spread germs to each other, right? If you look at this, there's a chart there that says end of the hour. So end of hour 1, 2 through 6, and the bacteria starting with 1. So at the end of 1 hour, since we started with 1 bacteria at what we consider 0 hour, there's 2. And so it's doubling every hour, which is what exponential growth is. So this is actually taking 2. You'll see the pattern is listed right here. So 2 to the first, 2 squared, 2 cubed, 2 to the fourth, and going through. And I have the chart here. I have one that's zoomed in so you can see a little bit more how we drew ours in the last lesson. That's kind of how we would sketch it. But then I zoomed out so you could see actually the question. It says our x-axis they label as number of hours that have passed, and our y-axis is the number of bacteria. So our question says, after 14 hours, estimate the number of bacteria cells. So I'm going to go with my 14, and right here we're going to have to estimate that. I'm going to say it's about 16,500. So after 14 hours, which would be less than a day, of course, we're going to estimate that there is approximately 16,500 bacteria cells. So you can see why when people are talking about the spreading of germs and how you should clean things to eliminate that bacteria, washing your hands between classes. If you're sitting at a desk with someone who was sick and had, let's say, like the flu virus, if they're at that desk and they have that illness, they're contagious before the symptoms always appear. If you're not washing your hands, think of where you touch your face constantly. You're touching your mouth. Your hands are all over your body, actually, if you really pay attention to it. By touching that desk and doing your math homework and then touching your face later on, that's where you're getting sick, which is why hand washing is probably the best thing you can do to eliminate those bacteria or a virus or whatever you want to say that's going to be going through and not having that enter your system. So, 2 kind of easy problems just reading graphs, but if you look at the problem, the word problem that goes along with it, hopefully you can see where this would be used in everyday life. These are problems that come up quite often actually, and exponential growth and decay. If you're going to be a science major at all, you will do a lot of work with that. So if you have any questions on that, you can let me know tomorrow.